So what we have been doing so far was to discuss about what is a Bayesian tracking. Now today what I want to do is to find how to analytically get the related equations that are ruling how to set the Bayesian tracking. Now if you remember, to make a Bayesian tracking, what I need to do, I need two equations. One equation which is describing the relationship between the state, the parameter called state, because they're changing in time. So the state, and then the second part, the second equation is the evolution of the state, which is describing how the state evolves from one iteration to another. So from one time sample to another. So then there are two relationships. Now the first one, which is the relationship between the observation of the data and the state, actually is the intrinsic relationship, which is part of any estimation problem. So you need to have the data, which is x, and then you need to put the data in relationship with the parameter, which is theta, and then knowing some statistical properties of the impairment, which is beta, then you can get the theta, okay? And then what we discuss is that in case we know some a priori distribution of theta, then we can estimate the theta using a Bayesian method. In case we don't have any a priori information on theta, then we assume we are using a maximum likelihood estimation method. So depending on whichever condition, we have been using just the first. Now the new one, okay, is that now we have an equation which describes the relationship between the evolution of the state in time. So this is given by this second totally new representation equation, which is describing how the state at the iteration n-1 is evolving into the state at iteration n. Remember, n can be, so the iteration n can be the time sample, okay, or group of time sample. So we call time, if you like, which is more easy to capture the meaning. Then that means that once I know the state, which means the parameter at iteration n-1, or the time n-1, I can get the state at the time n, which depends on according to the function that is known, and then it contains some alpha. Alpha is a random term which is exciting, so it's in some way making the capability to get the evolution of the state at time n as dependent on the evolution or at the state at time n-1, plus one term which is not predictable. So this evolution, according to the fact that alpha is a random term, this makes the evolution of the states contain some unpredictable behavior. Now, if alpha is equal to 0, then everything is perfectly predictable. But the alpha is different from 0, which is stochastic. Then it's totally unpredictable, or at least within a certain accuracy region. Now, so beta is the data noise. It's the noise. Okay, we call it noise, and alpha is the excitation. Okay, they are both random. So random means they are characterized by their distribution or statistical parameter. Now my goal is to get the a posteriori PDF. So my goal is to get the probability density function of theta of the state at the time n, putting together the measurement about the data all the data from the sample 1 to the sample n. So you know, if I want to know what is the state now, I'm chaining. Okay, chaining means putting together. Okay, all the data from all the past, let's say virtually from time 1 to time sample 1 up to the current one. Okay. Now, so now still having this sketch on the top. So you remember the goal. Now, if I know the a posteriori probability, so that one is the a posteriori probability density function, time n, chaining all of the observation up to n, then I can get to the maximum posteriori and the minimum is whatever. The maximum posteriori is the maximum for this function, and the MMSE is the mean for this probability density. Okay, which are indicated here is the maximum or the mean. So now you know here in the notation, it's hot here. Here in the notation, okay, we are indicated as where when I'm using all the observation from the past up to the current one, okay, rather than using this heavy notation, you know, as theta n, you know, that depends on all the observation from 1 to the sample 1 to from the sample 1 to the sample n. Rather than saying this way, I compactly indicate by using this notation. Now, this notation indicates that theta is at the time n by using all the samples from 1 to n. Okay, so it's understood in this notation that here I'm using x1 to n. This is what is understood in this way of this kind of notation. Now, so right now, I mean, I'm just recollecting in formula what I was discussing in a tutorial way, okay, by making the movement of the target. If we are in a very special setting, which means if the a posteriori is Gaussian, okay, which in a compact notation indicates theta n given n, which means theta n given all the observation from 1 to n, okay. If this one is Gaussian, then I can represent by its mean and its covariance. Okay. So now, if that one is Gaussian, okay, so just to recall that this notation means x1 n. If this one is Gaussian, then it depends on the mean and covariance. Okay, it depends on the mean and covariance. Now, but you know, why am I indicating that this mean is x hat? Because if in a posteriori, okay, so remember, you know, we have the a posteriori, we are treating the a posteriori, okay? So remember, you know, if my probability of theta given x, this is the a posteriori, and you know, so the max coincide with the theta max. The mean coincide with the theta MMSE. But if Gaussian, then theta max coincide with theta MMSE. And then, you know, coincide with, now with Gaussian, okay, that means this is normal with a certain mu theta and a certain covariance with theta. Then this guy coincides with mu theta, which is the mean, okay? So that notation is saying that rather than putting here mu theta, I put theta MMSE. I could also put theta map. That's the same because they coincide. Okay. So don't be confused about the notation. Never be confused about the notation. The notation is only a way to describe the phenomenon. Okay. And remember, it's always very easy to confuse the ideas by playing with the notation. So don't be confused on that. So here, this description is so the a posteriori, okay, at the time n, given n, which means given all the data up to n, is Gaussian, and its mean coincides with the estimate. So this theta hat here, this one is the mean, which is the MMSE, which coincide with the map, because Gaussian, okay? And now what is this P theta given, Pn given n? This is the a posteriori, what? Covariance, okay? So this is the covariance for the a posteriori PDF. Which is Gaussian. Okay? So now, my goal, my objective, okay, is to see how to handle the Bayesian estimation, Bayesian tracking mostly here, okay, when everything is Gaussian. Now, but this everything Gaussian is a very special case, and when the Bayesian tracking when everything is Gaussian is called Kalman filter. So the Kalman filter is an estimator, is a Bayesian tracking, so it's an estimator for a time varying phenomenon when knowing the evolution of the state and the probability density functions are Gaussians. Now we remember that everything might be Gaussian if we have a linear system. Because in linear system, I manipulate Gaussians and then it's Gaussian. Okay? So now, being more precise, okay. No, I was skipping one step. I was skipping one step. Now, we discussed in a minute about what are the basic assumptions of Gaussian. Okay. Now our goal is, I told you that I have the a posteriori. So if I have the a posteriori, I know how to make everything, but how to get to the a posteriori. So in order to get to the a posteriori, what I need is that I need to put together the information that comes from the data on the previous iteration. So the Bayesian tracking is carried out by putting together one after the other the estimation carried out using the data up to a certain point. In other words, what I am going to do is this. I'm going to start from a certain a priori probability density function at iteration 0, which means when I don't have any data. Okay? And then, you see, this is the a priori of the a priori, if you like. So this is the a priori probability density function of the experiment, of the overall. Okay? So that means that is the a priori PDF, okay, of the overall tracking experiment. So if we are simulating the case that you are estimating and tracking my position, for instance, so the a priori is going to be uniform, if you like, within this group. Uniform means, that is it's everywhere inside here. You are not preferencing any position inside here. So fine. So you know that I'm inside. Then you put it as a uniform a priori distribution. You know that there is a lecture, so you put the a priori close to the board. Okay, so this is just to say. Then, once I start start with these a priori, then what I can calculate? I can calculate the a posteriori at the first time samples using the data from the first time sample. So far, we are calculating the posteriori at the first sample. Then, from here we move to calculate the posteriori in the second sample, and so forth, until we reach the position where we calculate the posteriori at the n-1 iteration. And then, I want to calculate the posteriori at iteration n. So now, rather than chaining all these set of estimated steps, I focus myself on the estimation between n-1 to n. Okay, because all the others are just repeating the same step. Now, so this is graphically, okay. So here graphically, what I'm going to do is this. Assume that I know the posteriori on the time samples n-1. Here the posteriori is coming from all the data up to n-1. Remember, having all the data is crucial for Bayesian tracking. Okay, so all the data up to n-1. Now, if I know this, okay, so this one is the a posteriori. At n-1. Okay? So, if I know the posteriori, then, I can calculate the mean, and this is the MMC. I can calculate the maximum, which is the MAP. Okay? So, for instance, having this a posteriori, which is clearly non-Gaussian. So, this case is the most general one. Look at here, don't look around. Okay? So, having that one, then I can calculate the MMC, or I can calculate the MAP. That would be theta MAP n-1 given n-1. Given means given all the data up to n-1. Okay, so I cut it down and say given n-1. Now how to calculate how to move from one step to another. Okay, remember, my goal here is to go from P theta n-1 given x1 n-1 to P theta n given x1 n. That's my goal. Okay, so how to make this sequence of steps. Now the way to make this sequence of steps, because these steps are divided into two steps. One step is called prediction. What is a prediction? We saw by moving the target, okay? The prediction is carried out without knowing the new data. So what I do here, since I know this probability density function, I try to predict, to say before it's prediction. I try to predict what is the distribution, so the probability density function of theta at a time n by using all the data up to n-1, so by using this. Okay? Now, how to move from here to there? Now, let me show you graphically, then the equations are just saying the same story, but let me show you the graphical. Every point here, every dot, okay, is representing the probability that I have that specific value of state. Now, if I want to predict, so if I want to move from time n-1 to time n, that means that every time I'm sitting on one state, okay, at the time n-1, I have a certain transition probability. This transition probability is telling to me, once I know that I am at a certain point, what is the probability that I'm going to be, or where I'm going to be at the time n, given that I was in n minus 1. In other words, if I'm here, then I mean, perhaps, imagine this is a movie, so I mean, I would be around at that point with a decreasing probability. This decreasing probability has this triangular shape. Now, let me represent it graphically, like a cartoon, okay? Imagine that, I'm staying at a certain point. I'm moving, okay? So I'm moving in a certain direction. Now, when I'm moving in a certain direction, now assume that about my movement, the probability density function of my position, okay? You need to move from the concept of knowing my position to the concept of having the probability density function of my position, which is another story, okay? Because if you know the probability density function of my position, you can estimate my position according to the MMC or MAPA criteria, okay? So that means that probably the probability density function of my position is a distribution around my true position if the estimate is unbiased. Anyway, so let's make it this way. So you need to imagine that, I'm walking with a kind of big dress, and this big dress around me is my PDF, okay? So now, imagine that I'm here. Now, and I'm moving in this direction. Now, where I'm going to be next? I'm going to be with the highest probability, okay, with the slowest probability there. So imagine I'm looking in front of me. So with the highest probability, if I'm walking this direction, keep walking straight. So with the highest probability, if I was in a certain point, at the time n minus 1, at the time n, I'm going to be continuing that direction. With a decreasing probability, I'm taking different route with a decreasing probability. And then, there is a close to zero probability that, rather than walking straight, I move in this direction. So, which means, I'm doing this way. Okay? You see? It's anomalous, even for you, If you see a person that is moving along the road, and then, immediately this person makes this anomalous movement, all the people fall down if you are in the metro, metropolitan here, okay? Because the people doesn't expect it. So everybody of you is predicting the movement of all the others, okay? And that's why you walk. So you walk in a crowd because you are predicting the movement of the others. And in the crowd, the people, you are expecting that is moving according to the crowd. If you are moving unexpectedly, then the people start falling down, okay? Because you are not behaving as the other people are expecting, okay? And this reasoning is also can be applied to the road, to the cars moving, and so on, okay? So, like the people moving on the street. When the people moving on the street, and there are cars moving around, the people can do a more sharp movement with respect to the car, because the car is constrained to have a certain radius of curvature, okay? And then the speed and the inertia of the car is different with respect to the people. Now, going to the point. So, how can I say that to solve it? Now, I'm going to say the following way. Now, my transition probability, now look at this as a transition probability. My transition probability says the following. If I was at a certain point at a certain time, and the next time, with higher probability, I stay there. Then, with a decreasing probability, I am moving on the side. On the side, on the right side, on the side means on the left side. Okay? Now, up to the point, up to the value that, this 0 might be the length of your leg. Okay? So there is 0 probability that, if I'm here, okay, at the next step I'm going to be there. because of my leg, there are physical constraints, okay? So now, I'm talking about physical constraints, okay? So that means that in order to describe this prediction, I need to put the physics of the adaptation of the parameter. In other words, this is the predictions carried out according to the physics of the movement, according to the physics of the evolution of the state. Okay, here I'm using the equation which is mapping the state evolution. So from theta n minus 1 to theta n, and this is the evolution of the state. This is, let me say, the new equation. I'm using a new equation. Now, but what's happened when I do this step? Now, the technical way to do it, we will see in a minute. But what I need the probability of the state at the time n, given that the state was theta at the time n minus 1. In some setting, this transition probability, the technical name is transition probability, now this transition probability in some setting is dependent on just on the difference between the two values of the states. Okay? Now, what do we get after doing that? I told you, mathematically we will see in a minute. What do I get after that? I get the probability of theta, so is the probability on theta according to the data up to n minus 1. Okay? So this is the reason why it's a prediction, because I'm predicting, I'm saying before collecting the data. Okay? This is the prediction. Now what I do is I use this prediction as the a priori. So this is the real conceptual step. This one that is obtained by manipulating at the a posteriori at the time n minus 1 becomes the a priori for the next step. So this becomes the a priori PDF. This is the conceptual part. Becomes a priori PDF for theta n. Right? This is new. Let me say, there are two new steps here, two new conceptual steps. One is this one that I'm using a new equation, and the second conceptual step is that the computation through the transition probability is used as the a priori probability density function for the next step. Now, if I know the a priori, okay, if I know the a priori, so if I know the a priori, if I multiply the a priori with the conditional PDF, then I get the p theta here. So I get the a posteriori using the a priori by the bias formula up to a gamma, which is a scaling, okay, which sets the distribution correctly. Now, so that means that if that one is the a priori, I multiply that one by the conditional probability density function, which is this one. Now, this conditional probability density function is computed locally by observing just the current sample xn and the theta n. Now, putting these together, this was the basis for computing the maximum likelihood. Because if I take and I maximize this a posteriori, this conditional probability density function, maximization of of this conditional probability density function is the maximal likelihood estimate. Okay? So putting together means I take this one, multiply by that. I multiply value by value, sample by sample, this one times that. And you know, and by multiplication, what I got is a new behavior. And the mean for this new behavior is the MMSE estimate. And the maximum is the MAP. So that's how you know the tracking is carried out by a first step, which is the prediction, and then you know here I'm using the relationship which is putting together the parameter and the data. So here I'm using the data. So here I'm using, you know, for the update I'm using Excel, which is the data. Okay. Now, let's see how these two steps might be evolved. Okay, so let's see the analytical relationship. Now, the prediction is the first one, okay, which is this one. Okay. So for the prediction, we say that, you know, this one is known, and what we want to get, we want to predict. Okay. So that means that prediction says that I want to go from the posteriori at the step n-1, and then I want to find the probability of theta at the time n, given all the data up to the current one. I'm not using the sample, the last sample. Now, to update that, you know, I'm using the Chapman-Kolmogorov equation. Chapman-Kolmogorov is putting in equation what I was intuitively telling you, which means reading together. Is the integral fine of what? Of the a posteriori at the time n-1. Okay. Now, reading together. This means that for any sample of the a posteriori, this is spread into a certain interval of the predicted value. So the a posteriori value at the time theta n-1 is distributed according to the transition probability to the probability density function of, which is here, of the parameter at the time. In other words, that means that if imagine as ideally, I have a kind of a posteriori probability density function, which is a delta line. Okay, it's a delta. It's the idea of Dirac delta. Okay, so where is the professor? He's here. Is there any uncertainty? No uncertainty. I have a delta. Is here. Maximum and MMC coincide. Perfect. I'm here. Now, but since I'm moving in that direction, where I'm going to be next? So you know, the position where I'm going to be is sprayed. So it's like it's distributed with a certain cone, because I can go straight with higher probability, but you know, I can move right, left, and so on. So if ideally, you know, your or my probability density function, so P, this is a two-dimensional, okay? This is theta 1, this is theta 2. So if P theta n is a delta theta minus theta 0, let's say. This is ideal, okay? So if I'm sure that I'm here, this is theta 0. Okay. So where I'm going to be next? Well, I'm going to be with higher probability straight, with lower probability this direction, lower, 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 okay, and so on. So it comes out that, in the next, my transition probability is a triangle. Because, after one step, I am sprayed. It's like a spray. Okay? I'm sprayed within a certain cone with the highest probability straight, but a decreasing probability around the maximum value. Okay? Of course, there is not just this transition probability, which is a triangular one. It might be triangular, it might be different. Okay? For instance, if I assume that my transition probability accounts the possibility that I don't move, then it's not a triangle, it's a triangle with a delta on the top, right? So it can be exponential, it can be double exponential, so it depends on the case. It depends on the application, technically. So anyway, reading that, what I personally read, I read in this formula that every state at time n-1 is distributed to a time, to the theta at the time n, by taking into account this transition probability as part of the probability which is distributing the corresponding value of the state from n-1 to n. Now, to solve this, the Chapman-Kolmogorov integral, you need to know it depends on the state evolution. Please remember that. Okay. Surely, if you come to make the order, okay, because I want to specifically, exactly know what is contributing to what. Okay, because at the end of the story, you know the formula for Kalman or for Bayesian tracking, but I want to have a clear understanding where they are coming from. So this one depends. You see, it depends on the state evolution, because you see you have theta, and alpha. That's it. You don't have the data. Here I'm not using the data in the prediction. Now, as I said, for the special case, okay, in some common settings, for some special case, that this transition probability depends just on the difference of the position of the state, without dependency on the absolute value of n, then in my Chapman-Kolmogorov simplifies into a convolutional relationship. So it's a convolution between the transition probability and the a posteriori one. Okay? So most of the cases in this way, okay, except for some special settings. So it depends, on the problem. So I cannot state as a very, very general that the transition probability is always independent on the absolute time. Now I tell you, just to release the mood, I tell you a joke. It was many years ago. Okay, many years ago, we were working on a radar tracking. Okay, and so when we developed this new tracking method, me and my colleague, and essentially we were assuming that the transition probability was not dependent on the absolute time. And this means that we had to implement this formula. Okay? So, that means that if you implemented this formula, so this one is a transition probability, which is normalized to 1, and the other is a posteriori probability, which is normalized to 1. And so this one is a convolution, right? So what you expect, it's not like here, there is this gamma which fits everything, okay? So that gamma there makes the distribution to be normalized to 1. But here it has to come exactly normalized to 1. So then, we implemented, actually we had no MATLAB at that time, okay? So we implemented we use a foreground there. So, it's a language we don't use anymore, but at that time everybody were using these, the coding was done that way. And so we implemented that, and so what happened? It happens that the the a priori, so there this probability here, okay, was not normalized to 1. And by the way, it was not only normalized to 1 in some cases. In some cases, it was decreasing. So, you know, and then we got crazy on that, okay? Because this probability should be normalized to 1. You know, if it is decreasing, then since there was also a mechanism, a double mechanism for tracking and detection, so, you know, that probability decreasing we started to lose the targets, okay? Which means, you know, you have an airplane, you track an airplane, then after a certain time, the airplane is there, but the algorithm was detecting nothing, okay? So then, you know, we couldn't understand why. So, you know, it's like in many cases, you start doing that, okay, it's fine, this is fine, you know, it's a convolution, come on, it's only a convolution. So, you know, everybody does a convolution. So at that time, you know, it was important. So at that time, everybody was, each of us has developed a piece of code, so, you know, we started to develop this code, that code, and so on. And so I and everybody in our group was using the convolution library that I created in Fortran. Okay? And the name of the function was crosscore. Okay, now is MATLAB is called Xcode, right? Okay, so I called the crosscore. Okay, and so, you know, that was crosscore for my library. Okay, fine. And, you know, I wrote the function in such a way that I was using the FFT because of making it fast, blah blah blah. But you know, that's it. So what happened? It happens that my function was wrong. Actually, it was wrong only on one sample. So I put everything right except one sample. You know, when you make a convolution, everything is fine, but you know, you never look at the last sample of the convolution. Here, the last sample matters. So what I realized that my crosscore was wrong up to one sample. One sample was wrong. So then, you know, there was a few days of panic because all the others in the group has been using my code. And so, knowing that my crosscore was wrong, so, you know, it was a panic for everybody. And then, so we tested again, so we rewrote, retested, you know, it was not impacting of any other, except to us. And for us, it was only because our distribution, okay, so these a priori, which is the a priori for the next step, should be normalized to 1. Okay? So panic, you know, I remember that. Okay, so anyway, just to tell you, you know, that's as a cross-check. Now, now you understand probably why every time you use like a Simulink, Simulink is fine, but you know, in some special condition, if I need to put my name on the project, which means if I take a responsibility of that project, and you know, I'm testing some very special condition, I need to know perfectly what's happening. And this is what I learned after my crosscore function, okay, that everybody was using. So sometimes, you know, I might be maniac, but paranoid, but if I put my name on the project, I want to check every block to be sure that the block does what it's supposed to do, okay? I never take a code and accept the code of someone else as for granted. I need to make some cross-check. And one of the privileged cross-check is to compare with the CRB. Okay? If it is, for instance, if it is much, much bigger than CRB, then I say, okay, you know, we can do better. If it's going lower than the CRB, there's something strange. Okay? Perhaps I made a mistake on my CRB, but you know, perhaps the way I define the SNR is different between me and the other, but that's one point. Now, so let's see. So this is by the prediction. So as I told you, you know, that we are completing this step. Now, this probability is becoming now the a priori. And so what I calculate here is by the prediction step, is the a priori for the next step. And so what's happening in the next step? In the next step, I make the update. So, I give the a priori calculated, okay? So the a priori is now known. And then my goal is to calculate the a posteriori, okay, at the step n. Now I have the a priori is known, but this is the a priori at the step n. So I'm perfectly matched with the Bayesian estimation. I know the a priori probability, and I want to get the a posteriori probability. So how do we do? Bias, right? So, that's simply bias. So by bias, this is, where is it? Here, that's the normalization. But apart from the normalization, this is what I calculated. Let me highlight with colors. Let me see if I'm not messing up. Okay, yes, you see. So this one is the one that I calculate here. Okay. Then I need the conditional probability density function, which is the one that I calculate here. Okay, which is the one that we currently use for maximum likelihood. What is it? Don't be messy with the index. What is a maximum likelihood? I need to write the probability of the observation given the parameter. Okay? That's the maximum likelihood. The only difference about this maximum likelihood function that I might get from here is that there is all the other terms. But this is coming from the fact that this special, let me say, likelihood function has been obtained by chaining all the observations. I'm using all the observations. So this one is telling, okay, that this is the probability density function of x. Given that I know theta, and I know all the data before. I know all the data before. They are deterministic because I have already, once observed, they are deterministic. Remember, a data before observing is random, you don't know, but after you observe, it's deterministic. Okay? So, and that one is what I computed from the previous step. Okay? So this is chaining all together. And that one is, as I said, you can put normalization. Okay. No, I would say it's finished. There is no other to say.
So in the green part of the equation, so what's the weight of the x from 1 to n minus 1 if I already know the data? And I could also...
that's, the way of writing, okay? You are contesting this way of writing, right?
Yeah, the x could also be removed, I think, if I know the data.
Oh, yes.
Okay.
Yeah, you're right. It's not necessary, so that's probably because I was too packed. This one is not dependent. Okay, this one is not dependent on that. You're right.
Okay, so
I'm using the local value of the probability of the dependency of the relationship between x and theta. Okay, in a special case. But the main reason is from the proof. Okay, so since p theta, what I want to get is p theta depending on all the observation. Now I can chain, I can divide the x 1 to n into x 1 to n minus 1 and then the last one. Okay. And now, since I want to change that, so I want to rewrite the conditioning, not just with theta, but I want to write a joint probability of theta and x. So I put the conditioning here, which is what you see here. And then, since I'm writing the condition, this goes into the denominator. Then I'm splitting that. So I have a theta n given x n, and then all the other, and then I have a p, I have a p theta given all the others without x. It's still. Okay. Then the next step can be, but now this is local. Okay, it's not depending on the chain of the data. Then it is here. Okay. Good. Yeah, it's here. See it. So to compute, okay, this is summarizing, my properties. So to compute these update, I need the relationship between the data and theta. The data which is x and theta which is parameter. Now, this relationship is the one that I conventionally use for making, for instance, non-Bayesian estimation, because I'm using the relationship between the data x and the parameter t. Now, to move forward, in principle, I can implement these relationships for whatever dimension of the problem. Now, that one is becoming too complex in some setting. So this is, by the way, this is the most general way. So to make it more practical, I make some assumption. Assumption number one is that, if everything is Gaussian, then I can get some closed form relationship. If everything is Gaussian. And then second, so maximum Laplace is more noisy, but we already discussed. So let's point on that. Let's see the closed form. But the closed form for Gaussian setting is only when I'm in Gaussian context. So how is this Gaussian context? Now let's move into the Kalman filter. Now the Gaussian context is when I have a special but very common setting where I have the two equations that I was describing. The equation which is describing the evolution of the state is linear. In other words, what's happening is the following. The state at iteration n is depending on the state at iteration n-1 up to a linear filtering, okay, the linear transformation A, and then there is an addition, there is the excitation alpha, which I put here. Okay. This is how the state is evolving. Now, looking at the state, this guy is evolving independently. Okay, this is going on independently. So it's how the state is evolving. So you can consider how a person is moving, how a missile is moving, how a car is moving, and so on. Okay, so it's how the state is evolving. Now the state is evolving in an unpredictable way according to the alpha factor. So the excitation. If there is no alpha, it's perfectly predictable. But due to the presence of alpha, this evolution is not predictable. Now, let me make an example here, so it's clear the concept of predictability and not predictability. Now imagine that we are throwing a stone. Okay. Now my goal is, or I can shoot a rifle or whatever. Okay. So if I throw a stone, the stone is doing this way. Okay. Now the trajectory is perfectly predictable. Okay. So if I consider this as is theta n, as the position of the stone in this plane. The position where the stone is dropping is perfectly predictable. I know perfectly where the stone is dropping. Okay? But you know, this is the evolution of the state. So, if I describe this evolution, this can be described even if it's, I don't know if it is linear, but you know, probably it's linear in either. Let me not guess. But you know, let's say that this one is a theta n minus 1. Okay? So this behavior, let's assume it's linear. Okay? So I know perfectly where the stone is dropping. Okay? So that means that in my equation there is no uncertainty. There is no excitation. Once I throw the stone, then it's evolving. Okay? But as the have you seen Sniper, the movie? Okay? Which is shooting very far away. Sniper. Sniper, okay. You know, you're shooting, and then you know, when you shoot, you need to take into account about the wind. Right? So the wind makes this movement somewhat unpredictable. I'm exaggerating. Okay? So you know where it's going, but not exactly. So what I can say is that, you know, I mean, this dropping point, perhaps, you know, is where I'm predicting, but, you know, perhaps it's distributing the dropping point with a certain uncertainty. Now, alpha n is the wind. Okay, just to figure out. Is the wind that makes the overall trajectory unpredictable. Alpha n is also the position of the initial condition. If I'm throwing a certain way or the other way, you know, it makes an impact. Okay? So these are some uncertainty. Now, these uncertainties taken into account by alpha, okay, which is the excitation of the evolution of the dynamic of the system. And we're talking about it first. Now, the second one is a linear relationship between observation and theta, the parameter. Now, if you look at what we have been doing previously, this is the common equation that we are dealing with. Now, I open the page before coming. Here it is. Okay. Look at here. Look at together. I have x is the data equal h is the linear transformation time theta plus w. Okay, w is the noise. Now, and you know, if I know the a priori on theta, I can get the theta MMSE. If I have the noise which is Gaussian, this is Gaussian, this is Gaussian, this is Gaussian, this is Gaussian, then x is Gaussian. It's a linear transformation. So we are in a Gaussian setting, let me say it that way. So going back to our model, if beta is Gaussian and is part of the assumption, if b is constant or might be also varying, but is linear. Now, the only I need to know is the a priori on theta. Okay? So if I know the a priori, this problem of estimating theta, knowing the a priori, is exactly the problem that I just showed you here. Now, so what are the assumptions for Kalman filter? So I have a set of parameters, p parameter, and I know A, which is the evolution of the state, and I don't know alpha, but I know only statistically alpha. And I assume that alpha, okay, which is the excitation of the dynamic evolution of the state, is characterized by a certain covariance, like zero mean, and characterized by a certain covariance, C alpha alpha. Further, so that means this guy is evolving itself. This guy is evolving within a certain behavior. Once I know the initial condition, I know where it's dropping with a certain, with some uncertainty. and I know the uncertainty. The uncertainty depends on alpha. Alpha is the wind. If the wind is strong, it's very uncertain where the stone is dropping. If the wind is very weak, then it's very highly predictable, but it still contains some uncertainty. Now, and also depends on beta. Now, this is the relationship between the parameter and the observation. And beta now plays the role of a noise. Okay? And so beta is also characterized by a certain covariance, C beta. Now, I would say now the Kalman filter is just a simple usage of the previous relationship, which is what we are going to do. So, as I said, the Kalman filter estimates the evolution of the states. I'm simply repeating, knowing the model, knowing the relationship input-output, knowing the covariance of the station, knowing the covariance of the noise. Okay? And what I need to do, I need to initialize. So initial condition is that I know for theta 0, which is the initial condition, okay, which is what I need. So I know that initially it's a normal with a certain 0 value and with a certain covariance. Okay. So this is the initial condition. Now we make a remark on that, but let's assume that it's a Gaussian. This is the classical Kalman filter assumption. Now, what we need to do is we need to find, we need to find the estimator. Now, here is what I already told you. So, what is the rationale for the MMC estimator in the Kalman filter to be linear? Okay, there's a provocative question. Now, it's linear because this guy is Gaussian. So, since this guy is Gaussian, when I initialize in 0 is Gaussian, so this is linear transformation, theta is Gaussian. If theta is Gaussian, it's linear, I have a beta is Gaussian, this is Gaussian. So everything is Gaussian. So it's Gaussians that keeps moving inside. Okay. Okay. Now, how do I write my equations? Now, first of all, if you remember, we started from knowing p theta n minus 1, given all the observations for 1 to n minus 1. So we start from this one. So this is the initial condition for recursive Bayesian tracking for estimation procedure. This is what we need. So we assume that we know that. But if this guy is Gaussian, then this is equal, so it's a Gaussian distribution. So we say it's Gaussian with theta, theta n given n. It depends on a certain mean, but the mean is the estimated value, and with a certain covariance, n minus 1. So I have no rule. So, what I know is this. The a posteriori at the previous iteration is Gaussian. Here it is, it's too long to see. Now it's Gaussian, that's the variable, that's the mean because of the previous iteration was Gaussian, and the estimate is the map and MMSE. Because of the Gaussian. And the P is the a posteriori covariance at iteration n minus 1. Then, what I need to get is, I need to make a prediction. Now, what do I make with the by prediction? I want to estimate theta n, given all the observation up to n minus 1. But since everything is Gaussian, so what I expect that, this distribution is Gaussian with a certain mean and a certain covariance. Now the two covariances are different, so the notation is different. So here is a p n minus 1 given n minus 1, which means given all the data up to n minus 1. And here is the covariance n given all the samples up to n minus 1. Now this one is the a priori covariance. And this one, theta hat, is the a priori estimate. So it's the estimate of the position of the target of the parameter by using the predicted values. This is the prediction step. And then, we make the update. And the update, since by the update everything is Gaussian, so I have theta hat a posteriori and p, and n. Okay. So, but look at here, if we are dealing with Gaussians, then my set of parameters to play with is the mean or the estimate, the covariance, okay, the posteriori covariance iteration n minus 1, the predicted value, and the a priori at the step n, which is, obtained by the prediction. And that, again, is, so have the similar, so the dual part, and then again, so that means that it's enough for Kalman filter to update the moments, because since I'm dealing with the Gaussian, so the Gaussian is all completely described by the moments. Now, so this is just a notation, so we already described. Okay, so how to make a prediction in a Kalman filter? Now, in a Kalman filter, the prediction is obtained by knowing, so I know the a posteriori at iteration n minus 1. Okay, so this is known and this is Gaussian. So since it's Gaussian, for the prediction step, I need to use the formula which is telling me how the state is evolving. Okay. So the formula which is describing how the state is evolving, so let me just recall it here. So it's theta n equal to a theta n minus 1 plus alpha n. This is the equation of the evolution of the state. I'm using that. So now, in my equation, do I know theta n minus 1? Actually, I don't know theta n minus 1. I know its distribution. So, I can obtain the distribution of theta n, knowing the distribution of theta n minus 1 and the distribution of alpha. So, in this equation, I know what is known is that this guy is normal, and this one is represented by theta n minus 1 in all the samples up to n minus 1. So, I know that this one is Gaussian. So since this one is Gaussian, if I ask you, what is theta n? It's Gaussian. What is the mean value of theta n? Is A, the mean of this, plus the mean of alpha, which is 0. Okay, so what is the mean value? So the mean value here is A times the mean value of theta n minus 1, which is 0. What is the covariance of theta? The covariance of theta is the covariance of this guy pre-multiplied, post-multiplied by A and A transpose plus the covariance of alpha. And that's what is written here. So, Now, you know, once I apply these two relationships, I mean, I know all the properties of this theta n, which is now is the theta which is obtained by the prediction model.
So after every prediction, we have the covariance at time and predicted,
You're right.
Which is larger always than the
Yeah,
covariance
because
at previous system.
yeah, what we are doing, I mean, the reason why I was discussing so much about this plot is the following. So, you know, we are, assume we are here, this is theta n minus 1, n minus 1, and this is the covariance n minus 1, n minus 1, okay, which is, let me say, a certain degree of uncertainty. When I make a prediction, okay, forward, now my, let me say, my covariance is bigger, okay, because I mean I'm summing up the uncertainty of the prediction with the uncertainty of the evolution of the state. Okay, that's here. When I put together the maximum, let me say, the Laplace function, which is not the conditional probability, then I get a shrinked one. So what I do is this: I have a certain PDF, okay, which where the mean is corresponding to the estimated value. I make a prediction, my PDF is getting bigger, and the center, which is the mean, corresponds to the predicted value, okay? And this one, the ellipses, which is I am representing graphically by hand, is describing the predicted covariance, okay? Now, this predicted covariance, the covariance for the predicted value, is the a priori for the next step. Because the next step, if I don't put this as a priori, it can go everywhere. Now, after putting the data, okay, the covariance gets smaller. Okay? Then again, bigger, smaller, and so on. Okay? This is predicted, okay, update, predicted, update, predicted, update, predicted, update, so on. By the way, this is what is in your phone. Huh? Okay, have you seen the circle? When you try to locate, to find your position, okay? It's doing this way because, I mean, in that case, the phone is using additional information. I mean, GPS, for instance, we will talk on that, but you know, for GPS, in case you have a, I don't know, you're using a certain amount of satellites or a certain number of satellites, and you get some uncertainty. If you have an additional satellite which you might gain the visibility, then uncertainty reduces. If you are listening to an access point, okay, which on some database that you know is known by the guide which is making the map, then your uncertainty is reducing. So if you have seen, you know, it's keep moving, and the point, if you are indoor, it keeps moving at the point itself. The reason for the point moving is because you are indoor and you have a multiplier. Perhaps we'll talk about that. Okay, so this is the description there. Now, so we found that the prediction is fine. So you know, it's, let me say, it's the easy step. Okay, the prediction. So these two are two of the equation which is used for a Kalman filter. Okay. Now we completed the prediction. Now what about the update? Correction. Okay. What is the equation for the update? Now in the update, what I'm using, okay, I have it. So what I'm using these, now this equation, which is xn is equal to b theta n plus beta. But now, in place of this b theta n, I have a theta, you know, I have the a priori from theta n given n minus 1. So I'm using the information a priori coming from the predicted value of the previous step. Now, looking at this problem, so that means I have the data, I have B, I know. I don't know this, but I know it's a priori probability. I know the statistical property of beta. Okay? Now, look with me. So that model is the same as x equals h times theta plus w. And in Bayesian estimation, I said, I know about theta. I know that this one is a certain mean and a certain a priori covariance. This is the a priori information. I know about W, that is normal with a certain mean and then a certain covariance. Okay? This is known, so once I get the measurement, I can get the data. Okay? This is from what you are supposed to know. That. Okay? This is from what you are supposed to know. So when I tell you about this new problem, you should not be surprised. And so, what is the behavior of the theta MMC? Well, theta MMC is the mean, then it's all this manipulation times x minus h times the mean of theta. This is the MMC. And and I also have a covariance. Okay? The covariance of the posteriori. And the covariance of the posteriori is the covariance of the a priori minus something. In fact, what I say that, my covariance of a posteriori should be smaller than the covariance a priori. Otherwise, there is no reason to make a measurement. Okay? This is what we have seen. So, now, let's take that and apply it. Now, what is the difference there? The only difference is that, the a priori is not given by God. It's calculated by the previous steps. Okay? So it's not that there is a genie which is giving me the a priori. It is from the previous step. So from the previous steps, I get the a priori. Now, putting it this way, there is nothing new on that, except that, the notation is getting too long, but there is nothing new on that. So, putting it this way, okay, the a posteriori can be easily derived. And the a posteriori is by modeling, this theta n, which is the a posteriori. So this a posteriori as a mean, and this mean, where can I write? One second. So, same problem as, what chapter is this? Chapter 11. Let me put slide with God. Okay? This is clear. Now, I have no other possibility. In order to put in the parallelism, I could write on the board and then, write there. Okay? So, it's just, you make the mapping. Okay? So, when you make the mapping about the corresponding relationship, then you get the MMSC. And so the MMC is long, but it's long this one, but it's similarly long that one, you see? Is it long? Okay, it's long. It's long. Now, let's read together. Okay, now, the theta MMC is equal to the theta MMC, the theta hat n minus 1. Now, this one is the predicted value. So I take the predicted one, Then what is the second term? The second term here, this one is x minus b theta hat n minus 1. Now, this is x is the data minus b theta hat. So b is the relationship. So it's like if I make the difference between this and that. So I plug in place of this value, I plug in theta hat n minus 1, which is the predicted value. So that one is the prediction error at iteration n using the data up to n minus 1. That is a prediction error. Multiplied by blah blah blah. This one is called Kalman filter gain. So writing in a compact way, the up-to-date is simply given by that. So it is the theta hat iteration at the time n, given all the observation up to n, is equal to the predicted value plus a correction, which is given by a gain, which is g, that is computed there, multiplied by the error. So the error is the prediction error. So I assume I predict, but by predicting I make an error, and this is mapping into there. So that means that what I do, I have the a posteriori with a certain uncertainty. Then I try to predict, which means my uncertainty is very big, and this is the estimate. When I use the data, my estimate is a little bit corrected from that. This correction, okay, which is the second term g time epsilon, this correction comes from a gain, which is the parameter that depends on MMC, and the error. And this error is coming from comparing my new data with these predicted output coming from the predicted value, which is b time theta hat and so on. Okay, so then it's carried out in this way. So I'm here, what I do, I'm predicting, and then I'm correcting, and I get a new estimate. But then I also told you that when I do the prediction, my uncertainty is getting bigger. Then when I have a new data, I have a correction, which is shrinking the covariance. So I need to calculate the covariance, but the covariance is calculated by using the same relationship for the formula on the chapter 11, which means my covariance is the covariance of the predicted, but the predicted is the a priori then. And then there is minus blah 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 blah. Now this minus blah 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 makes the covariance a priori, which is the covariance of the predicted, shrink, reduce. Okay. Now this one is called the Riccati equation in Kalman filter general. But it's quite straightforward by chaining all the set of operation one after the other. Now, what is more expensive in Kalman filter is the computation of the gain. Because the gain, the size of the gain matrix is very big. Okay, because it's the size of the matrix, is manipulating it has a dimension of the data that I am using, because it's multiplying x, so it has a size of x, and x might be big. And at every iteration I need to invert to this, And this one is coming from these a priori covariance, which might be variable. And so because of that, I need to update my gain step by step. And this is the most time consuming part. There is no trick. It's not like RLS, where in RLS you can use the trick that you have the update on range 1. There is no trick you can use. There are some tricks, there is no magic trick that is helping to make the common filter gain to cost not much. So to summarize, putting one after the other, okay? So the set of recursive equation is the following. So on the prediction, I need to update the mean, update the covariance of the prediction. This comes from the prediction. And then, this comes from the update. From the update, I have here the correction, okay, which means that the a priori value is corrected by the error. And then I update the covariance matrix for the a priori using the posteriori using the priori. And everything is ruled by the common filter gain, which is here, and it has to be computed. Everything after initialization. So all these makes the common filter set of common filter equation. Keep in mind that initialization must be known. Initialization must be available. Without initialization, it's the set of equations are not complete. Common filter is not complete. You cannot make a Bayesian tracking without initializing. And I guess we are a set of remarks. Let me go through the remark. First of all, common filter is optimal MMC estimator for linear model and Gaussian process, no matter if time varying. Okay, so it's the best you can do for everything. When it is linear, that's the best you can do. So common filter is the MMC, is the best estimator we can ever do if we are in a linear setting. A common filter is suboptimal in other settings, such as extended common filter. We will talk not tomorrow because I want to start a new topic tomorrow. We'll talk next week. Second, common filter gain is complex. Okay, so the complexity is in the order of n cubic, where n is the size of the data observation. Common filter is optimum even for time varying. So even if my matrix is depending on time, the common filter is still optimal. Now, we can also use the common filter in some degenerate cases. So I can use the common filter gain if alpha is equal to 0. Like here, assume the case that there is no wind. And if there is no wind, the stone drops there. Perfect, okay? But imagine that, my goal is to predict, is to estimate where the stone is dropping. Okay, that's my goal. Now I want to estimate where is this point. That's my goal. Now what I do, I make a set of observations. So I look at here, I look at here, I look at here, I look at here. Since my measurements are noisy, so then I measure x1, I measure x2, I measure x3. Okay. So what's happened is that x is noisy. Okay. Then if x is noisy, but the evolution of the state is not noisy, I can still use the common filter. And it's highly beneficial because what you do intuitively, I say, if I put together all of my data, then I can better estimate the position where the stone is dropping, And And we also know from the theory we have been doing so far is that the more parameter I estimate, the better, the more data I get, the better I estimate the dropping point. Okay? Now, I mean, this means that the Kalman filter here can be used to put together the data in such a way that the data are linked one after the other, following the evolution of the state, even if the state is evolving in a deterministic manner. Okay? Another way that you can use the Kalman filter is, I'm saying, some degenerate cases. Imagine that the state is not changing. Okay? So, I have xn is equal to b theta n plus theta n. Okay? Now, theta n, is not changing. So how do you write that theta n is not changing? You say that my state evolution is equal to identity times theta n minus 1. And putting in a extreme case is deterministic. Look at here. So that means that this plays the role of the matrix A, and I can estimate iteration by iteration the value of theta. Now, since the state is not evolving, in this degenerate case, what's happened? The more observation I put together, the better I estimate the parameter theta, which is not changing. That's a degenerate case. So I can use the Kalman filter even for this degenerate case. In the book, there is one solution for avoiding the update of the Kalman filter gain. That's one possibility. And as a last comment, which is a comment that sometime I ask to the oral. Now, assume that, let me go to the set of equations. Assume that I don't know the initialization. Okay? And assume, for instance, that the initialization are non-Gaussian. I initialize my model as a non-Gaussian. An easy way, I make it uniform. Where is the professor? Is inside in this room. So what does it mean? It means that the probability density function of the professor is uniform in this room. Okay? Uniform means uniform, right? Uniform is non-Gaussian, okay? Because it's not a bad, right? Okay, so that is non-Gaussian, okay? So initializing this in this way reflects to the maximal ignorance of the a priori model, except that I'm staying in this room. Now what I do, I make the Kalman filter evolving, because the evolution of the state is linear. So I let it Kalman filter go. Now, what is the mean? Is the mean for the uniform distribution. What is the covariance? Is the covariance for a uniform distribution. Fine. So, do you expect that the Kalman filter is going good, or do you expect that the Kalman filter is doing bad, or what? So, have you understood the issue? I initialize with uniform a Kalman filter, which is expecting everything to be Gaussian. Okay? So what's happened there?
Can we use this limit theorem?
Yes.
With our limitations?
Okay, so since you're using a central limit theorem, so what's happened is that, after manipulating linearly something, which means I put a non-Gaussian with a Gaussian, plus another plus, when I say plus, it means convolution with the PDF. Because the central limit says, if you sum infinite number of random variables with a comparable, mathematicians don't like that, with a comparable dispersion, okay? When I sum an infinite number of random variables with a independent random variables with a comparable dispersion, asymptotically, this sum behaves as a Gaussian. Okay? So this is what's happened. because I'm putting together. I mean, so if I initialize that way, then I mean I put there is all the steps is linear transformation, and even the model is linear. So I mean after certain amount of iteration, a certain amount of steps, everything becomes Gaussian. And so Gaussian visualization will be optimal after a certain time. After a certain time long enough. Meet you tomorrow then, huh?